Um, I just woke up, but let's let's just get into this. Um, okay, yesterday we did operator identity, continuity equation, like the total mass, the rate of decrease is equal to the change in density, basically. Um, Causes law changed a surface integral into a volume integral and back and forth. And you realize you can just generalize that kind of, is if that is the correct word, to you can just make it into, you can just um erase the thing it's acting on and just be like, oh, I'm changing the operator into a different operator, and it works out. And we have these a bunch of conclusions you can draw from that. Um, like this is equal to 3 times the volume and stuff like that. Okay, circulation, curl, and Stokes' theorem. The circulation bling of a vector field Fr along a closed curve, so a closed curve, is defined by the line integral this. So circulation of vector field, every point has a vector. So boom, vector here, vector here, vector here. Circulation is um, so for every point, oh, we're integrating the. Hmm, it's basically f dot dr. Is that it? Because f the x the x component of f and the x component of dr is dx. So this is this maybe maybe. Am I missing anything? We'll see. So circulation is just three integrals added up for each point, basically. Um, the part C contains a direction of integration. The counterclockwise, it is clockwise, this is counterclockwise. Direction being taken to be positive, so it is positive. Um, this is negative. The integral changes sign when its direction is reversed. The integral changes sign when its direction is reversed. Okay, C minus C. Okay. A helical pipe of helical radius A carries water at a constant speed v. The velocity circulation of the enters of flow in a counterclockwise direction is this. Let me see if I can remember what a helical pipe is. Helical pipe of helical radius A. Um, Helical pipe, helical radius A, maybe. I guess a really thin pipe. Like I read this a little before, and I thought the pipe was like a really thick pipe, and this was A, but I think A is just from the center of like what the pipe isn't actually there. The pipe is around the center. I could be wrong. Um, the velocity helical pipe of helical radius A carries water at a constant speed v. So it is V here, it is V here, it is V here. The velocity circulation. So velocity circulation. So there's different types of circulation. After n turns of flow in a counterclockwise direction is um hmm, and it looks like n, like if it's one turn, it's just this. If it's two turns, it's two times this. So it's that part is simple. Um, the velocity circulation of the end is a flow is this. So yeah, watch. It was just as I was saying, it's a dot product of effective field and dr. Okay, n turns. Um, so why not just say n and then boom for one loop via dr? Is that a good thing to say? I think it is. I feel so. Um, Vx dx was Vy dy. Why are we ignoring z? So the pipe. Okay. Hmm. I guess the argument is that the up and down, the up and down is negligible. Maybe. Maybe. Helical pipe radius. Helical. Like maybe the pipe is just a tube. Carriage the most circulation of the engines. So x equal a cos theta. Ah. Um. Okay, well, let me draw this. A. I could have drawn that straight up. Well, if it'll work, it'll work. A. A. I'll write the letters in a different color. A. This will be theta here. Theta A. Why is this A? Oh, because that's just what we have radius as. A cos theta doing um hmm. Cos theta equal adjacent over hypotenuse. So this is hypotenuse. This is adjacent. If A is the hypotenuse, then uh it will be like this. A is hypotenuse. This theta is here. Wait, no. That means here would be A. There's two ways to write A, I guess. Um, let me get rid of this. A is also this distance as well. But does that just make it worse? Either way, theta is over here. Theta is over here. And so no matter what, this distance here is opposite. So let me work with sine first. Y is opposite, and A is hypotenuse. Okay. Opposite. A is sine theta. Sine theta. Opposite. This will be Y. A over cos theta. Adjacent would be this little section here. I think it works out. So x equal a cos theta, y equal a sine theta. The velocity should be the differential, maybe, I would assume, because position into velocity. D dx, well, d theta would be sine theta and cos theta minus sine theta. A turns to V. A is radius. dA d theta. A V. We're differentiating by theta to get to turn it into this, but to change position to speed, you have to differentiate by time. So I don't trust in this too much. Vy equals V cos theta. Alright. So cos theta starts at 1 ohm. Sine theta starts at 0. I think this is how it goes. Ah, I think. I feel like it peaks at the middle here, and then something like this. Okay, so a sine theta. Let's say theta is 0. If theta is 0, then a is what? If theta is 0, then sine theta is 0. So y is 0. Oh yeah, that makes sense. So y is 0, that just means it's on this section right now. Cos theta is 1, a cos theta. So x equal a. So x equal a, y equals 0. So that means we're dealing with this point here, which makes sense because theta would be 0 at that point. And now velocity. The y component of the velocity would be v cos theta. Oh yeah, it makes sense. It makes sense. Because the tangent at this point would be straight up. So there'd be no x component of the velocity. I assume there's a mathematical way to get from here to here, but just from like dealing with the vectors and the tangents and stuff, you can model it to be like the model makes sense. Okay, let's just go back to this now. So circulation equal this. We found vxv minus v sine theta. This is minus v sine theta. V cos theta dx. We need to do it. We need to integrate this with respect to x. Vx dx minus v sine theta dx. But this is in theta and this is in x, so we need to either change this to x or change this to theta. And the easy way to do that is just using one of these things here. X equal a cos theta. y equal a sine theta. Y equal a sine theta, which means sine theta equal y on a. So we could just replace this with y on a. Um, this is still not an x. Uh, ah, y, y in terms of x. I bet there's some way to be like x squared plus y squared equal equal a squared. But I feel like that's too complicated. I could just be like, I can just like differentiate this with respect to theta, I think. So, um, dx d theta equal a cos theta d theta, which I believe is, it has been a while, I can't lie, minus a sine theta, maybe? Alright, so, um, minus a sine theta. So, if we like substitute all this stuff into here, dx equal a sine theta, negative a sine theta, multiplied by d theta. And we still have these guys, so it's minus v sine theta. You join these up, you get sine squared theta, um, minus va sine squared theta, which accounts for, well, minus and minus is a plus, um, which accounts for this term here. And I trust that if you do the same thing with vy dy, you'll get av cos squared theta. And we haven't really integrated. I just realized we haven't really integrated. We just changed the variable of integration. Okay, tools. Okay. Another way to visualize. Oh, wait. Before we go there. Sine squared plus cos squared is 1. So AV1, like the interval of 1 is just theta. And if we're going for, it's a closed circle. So we're going from here to here. So the starting point is the starting point 0, 2 pi? 2, I feel like the starting point is 2 pi and the ending point is 0. So, well, it's when you substitute that into theta, you just get 2 pi minus 0. So 2 pi times the constants outside times n will just be n 2 pi AV. Um, Another way to visualize the circulation is to consider a small rectangular closed loop. Small rectangular closed loop on the plane z equal constant, such as the one shown in figure 1.8. Figure 1.8. Well, where are you, my friend? I feel like this is too far up. 1.8? Okay. Screenshot. You go over here, paste, transform. Look how professional I am. Uh, Transform? Where are you? Transform. Okay. Um, Transform. Deselect. Go back to where I can draw. Yeah. Okay, let's go back. Maybe I should drink some water, who knows? I do not know. Um, okay. Another way to visualize circulation is to convey small rectangle closed loop on planes to equal constants such as this. Circulation is this. Um, and now we're going to integrate 4 times. One for here, one for here, one for here, one for here. Ah, hmm. So this is basically like 8 terms in disguise. One, is it? Well, I guess maybe some cancelled out because I'm seeing 6 here. 1, 2, 3. 1, 2. There's 3 in there. 3 times 1 is 3. 1, 2, 3. Yeah, 3 on top, 3 below. Um, blah blah blah. Okay. Do I really want to do this? Do I really want to do this? Oh, hmm. Okay. I guess I should. I guess I should. Um, so this is starting point, this is ending point. So this minus this. The integration is this minus this. But at the same time, it's just this little area here. X plus delta x. These values the same as these values we're going to get here. Well, we're dealing with 3x. So the velocity at this point, yeah, I think at the end of the day, we're just dealing with v dot dx. So this is just normal, like, length shenanigans. And this is just the, this is just whatever we're dealing with. Right now we're dealing with velocity. So I think this could work as dx for now. In this scenario, maybe. Um, so here, ah, well, let's see what this guy is doing. So delta x, which is this length here, delta x, um, uh, delta x, then we have x1, y, z. So z is constant, we don't need to worry about that. X1, y, z. So y, yeah. Yeah, this is just height. Delta x, this is the base, and this is the, hmm. Wait, I think it's v versus x, maybe? Hmm. I proved this to myself like earlier. Like I'm just like this section I'm basically just redoing. Like I trust that I know what to do. Blah blah blah. This is a cop out. Let's just continue. Circulation equal this. where xi, yi are suitable points on side I. Hence, circulation equal delta x delta y. This stuff, which is approximately del vx del y plus del vy del x. This. They just changed all the deltas into dels. Where the partials are calculated at a suitable point, x, y, z. Partials are calculated at a suitable point on or inside the rectangular part. On or inside the rectangular part. I guess at the end of the day, this is really, really small. So I guess the middle, like if you shift it to the left a little bit and to the right a little bit, it doesn't really matter, I guess. Cool. The right-hand side of equation this involves this. Hence, circulation is the circulation is just one component of this shenanigan. Delta x, delta y is delta z. I, j, k, del x, del y, del c. I'm just writing out this cross product to help me imagine this. Vx, Vy, Vz. They're saying the z component, like this entire thing is just, well, not the entire thing, just this section. It's just the z component. Z is this times this minus this times this. So del Vy, del x minus del Vx, del y, del Vx, del minus del Vx, del y plus del V, yeah, insane. Hence the circulation is just one component of this, where this is this, yeah. Circulation is the dot product of this. But they're saying here that the circulation is one component, and now they're saying the circulation is three components. Dot, bling bling, a dot product of something. Yeah, it's saying this is three components. The right hand side of this is this. Oh, I guess maybe, like over here we were just dealing with constant z. Like this is in a plane where z was constant. So it could be simpler to like do the math in. But in reality, z is not constant. Sometimes, or most of the times I would assume. So this turns into this. It makes sense. They pulled out the normal. That is normal stuff. But hence where n equal k here. Hence circulation is this. Where n equal k in this scenario. Is the normal to the surface, and is the normal to the surface. What surface are we dealing with? Closed loop. Closed loop. So technically this is the surface, I guess. Is the normal to the surface enclosed by the loop? I just need to finish. I should just read and then yap. Since a scalar product does not depend on the absolute orientation of the vectors, but only on their relative orientation. Like, even though these guys are oriented different, the scalar product is the same. It just depends on the angle and like the lengths of these guys, but only on their relative orientation. It is clear that the circulation is clear that this is actually independent of the choice of the coordinate system. As a consequence, the same result is obtained whether or not the small loop lies on the xy plane. It's actually independent of the choice of the coordinate system. So it doesn't matter that we did it on a plane. Same result could be obtained, is obtained whether or not it's on the plane. If we make the loop really, really small, if we now make the loop very, very small, I don't know why I'm drawing it. We obtain the identity this, delta this. Okay, this is the circulation. And we're making delta. We're making the surface element really, really small. Why? Why are we doing that? Let's let's just continue. So right now we have this equation. Makes sense. So we're just moving this across. So we have the curl of v dot n equal this, yeah. If we now make the loop really, really small, but why? We added this limit. Adding the limit. Okay, let's del VR, and let me just read. Okay. Thus, the curl of a vector field. This is the really insane um text, really insane sentence that I had to read it like 10 times to decode what it means at first. Um, like unironically 10. I'm not being exaggerating. Thus, the curl of a vector field VR, VR, vector field VR, so at a point it has a vector. At a point R in space, so this is the origin, and here to here is R. This is V of R here. The curl of V of R has the interpretation that its component along any direction n. So let's say n is in this direction. Let's say they're talking about the nth, the n component of VR. So Vn is given by this, the curl of this over here is just saying that the component along here is given by the circulation per unit, the circulation of this per unit area around a really small loop surrounding this point on a plane perpendicular to n. So there's a really small loop and it's on a plane perpendicular to n. The circulation of this, the curl of this just gives us the component of v in the n direction being the normal to the loop, the really small loop. Did I start out the sentence with circulation? Because the point is just to say it's equal to the circulation of this guy here. We move. Maybe I drink water. Maybe. Okay. Stokes' theorem. By subdividing a given closed loop, we have a closed loop, into small closed loops, like a lot of small loops, Ci, we find, is this circulation? We find that the circulation of the loop equals the sum, equals, so this is circulation. This is circulation of the really small loops inside of the loop. We pulled out this guy. This is circulation. And this is circulation divided by delta sigma. Is it sigma? I think it's sigma. Delta sigma I. But we also have delta sigma I here. So we get back circulation. This is just saying the sum, if we add up all the circulations of the small loops, we get the circulation of the big loop. Is that what it's saying? The sum of infinitesimals is basically integral. So integral plus integral is just double integral, so to enter surface. This integral relation is known as Stokes' theorem. It states that the circulation around a closed path is equal to the flow, oh my god, the flow of the curl across the enclosed area. So this is the enclosed area. That is, the circulation is caused by a flow of curl. Circulation is caused by a flow of curl. What? It's known as Stokes' theorem. It states that the circulation around a closed path is equal circulation rate plus what? This is equal to the flow of the curl across the enclosed area. So this is the curl here. Curl this little dot. I was going to say this little dot counts as divergence, but for divergence we need nabla to be here, the gradient function. Um, is there a gradient function in here? Can I like maths my way through this? Is there a secret nabla in here? Flow of curl. This is curl over here. Flow. What is flow? Did they ever say what flow is? Flow. N turns of flow. Turns of flow. This is what I don't like. Like they just introduced the word flow without really telling me what flow means. Um, the point is, let's just accept this as fact for now. Um, circulation is caused by flow of curl. And a close part equal to the flow of the curl. So that the gradient of a scalar field is irrotational. Okay, gradient of a scalar field. If something's irrotational, it means that the curl of that thing equals 0. Um, I think you can easily see this from like ijk del x del y del c del phi del x del phi del blah 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 blah. You can pull out the phi, which just leaves del x del y. And since these two columns are the same, this whole determinant is 0. So that's how I would prove it. Apparently you could do it Stokes' law as well. To change surface integral to a line integral. Where are you seeing integrals here? This can be done by using Stokes' theorem to change surface integral to a line integral. So they're using this operator. They're shoving in this. They're saying it's equal to what? They're using Stokes' theorem to change a surface integral to a line integral. Stokes' theorem. So we have like a cross, we have a curl, we have some curl shenanigans going on here. And this is also a curl shenanigans. So they shove the curl next to, they're shoving the curl inside the surface. And from Stokes' law, Stokes' theorem is equal to line integral dr dot the second term of the cross product. Not the second term of the cross product, the second term of the curl. Um, that probably means the same thing. The second thing, the thing that comes after cross. So dr dot this comes after the cross. So this makes sense so far. Equal this. What? Okay, so they changed this to this. We don't care about this anymore, apparently. We're just dealing with this right now. dr dot this. d5r. The integration variable became this somehow. Um, let's just compute. Let's just compute this dot product right now. dx multiplied by del x. Del x phi phi of r, just phi. I guess I'll add the r. Del x, del x. Let me change my color, like Michael Jackson. Del x, del x, dx, del x, dx, plus del y, dy, plus del z dz, del c dz. Um, I I think I see what they're going for. Like they want to cross out, they want to cancel out the dx with the del x. Can we do that though? Can we do that? I actually think we can because we're dealing with dr. So let's say this is r, which means this little piece is dx, and this little piece is dy, and del x is basically the same. Del x is basically the same thing as dx. Like they're both really small changes, but um, dx is smaller than dr, so it's not like we're saying dx. It's not like we're saying del x is dr. We're saying del x is dx, which is closer because this is smaller. So I guess we could say this is cancelled out. So we're just left with del phi. We're just left with closed curve, um, integration on a closed curve, del phi. Hmm. Del phi, 3 del phi? But this only has 1 del phi. It's not even del, it's d. But it looks as if they're interchange. They're treating del and d as interchangeable. So maybe that doesn't matter. The issue is I'm getting 3 del phi's here though. dr dot this. Del x, del phi, del x dx. We end up with del x. I mean del phi. Alright. Del phi del x. What we get after doing this is phi differentiated like with a little small x to note that it's in the x. We're only dealing with the x. But the issue is when you change this into an x guy, what I was going to do is just change this an x guy, call this a y guy, call this a z guy, combine them, to be like, oh, together they make up del phi. But in this process, you're losing. hmm, In this process, you're losing the del. Like at that point, it's just another function. It's just phi prime. Maybe I'm missing something. Hmm. hmm. Del phi. Okay, let's just try again. Right now, we have del phi, del x, dx. Is there any special cases we're doing here? Like, is there anything constant, like any planes? I don't think so. Show the gradient of a scalar field. Scalar field is irrotational. Scalar field. Scalar field. Does that say anything about this? So this guy doesn't really have any direction. He's just like a number. Maybe. Hmm. I'll come back to this later. Let's just assume this. Let's just assume somehow my theory where it's like they combine together to become del X. Let's assume that's correct. And we just do normal shenanigans, close curve, the beginning point and end point is the same. So just minus each other, you'll get 0. Where R0 is any point on C at which the closed curve can both begin and end. Since this result holds for any surface S, the gradient of this must be irrotational. And the fact that I did all this extra stuff, when I easily proved it here, it says a lot. Thus, a conservative force, which is derivable from a potential, is irrotational. The converse is also true, where the curl of a conservative force, which is derivable from a potential. So you can get a conservative force from a potential, or derivable, which is derivable is irrotational. So if you have some kind of potential field, you make like a force out of it, like doing gradient shenanigans. It'll be irrotational. The converse of this is also true, where the curl of the conservative force equals 0. F is conservative and is derivable from a potential. In fluid dynamics, the curl of a vector field Vr, which gives the velocity of the fluid at point r, is called its vorticity. So I think the velocity field is the conservative force field. I think that's what they're getting at. Vortices being the whirls one creates in a cup of coffee and stirring it. If the velocity field is derivable from potential, so if it isn't always, um, I think I should save this whole piece of thing here, this little nugget. Boom. Um, move this guy. Uh, you, you, transform, make you bigger. Ah, you transform, you deselect. If the velocity field is derivable for potential, which means you can get it from the gradient of just a normal scalar field, it must be irrotational according to um 1.5 equation 1. That's where is that? That is really high up. For this reason, an irrotational flow is also called a potential flow because you can get it from potential. Its circulation vanishes. So you can have a flow without a circulation, is what I'm getting from this. Irrotational flow is also called a potential flow. Its circulation vanishes. Being free of vortices and eddies, it describes a steady flow of the fluid. So the fluid is just going in one, like, it's not really curling around itself. I don't know. Like, it doesn't really. I'm just making up stuff, but in my defense, they are making up stuff too. They're saying flow, 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 and circulation, and curls and stuff. So I might not be that far from the truth. Being dust free of vortices and eddies, it describes a steady flow of fluid. One of our Maxwell equation is Ampere's law. This, the curl of magnetic field, I think, um, equal where B is a magnetic induction, J is a current density per unit area. Current density, so I per meter cubed, um, per, per meter cubed per meter squared, or just per meter squared? I think it just means per meter squared, maybe. And as a result, would be, so the curl of the magnetic induction gives us the the current density. Curl, so the amount of like movement of the magnetic field gives us more current density. Maybe. As a result, the current densities may be visualized as vortices of B. An application of Stokes' theorem to this gives Ampere's circuitry law. Um, what is Stokes' theorem? You can change between like for like the circulation, you can change between S and C, surface and line. Um, Ampere's circuitry law. CB dot D. So we have this. We have this guy. We're applying Stokes' theorem. I guess what I have to realize is that you can apply these like operator identities or whatever. You can apply these laws to stuff that doesn't really have integrals in them, I guess, because out of nowhere we get an integral here. A navigation of Stokes' theorem to this gives Ampere's circuitry law. Um, let me just screenshot Stokes' theorem. This looks kind of crazy, but we move. Uh, you uh um what? Oh, I have to select it first. Select you transform make bigger. Where do I put this guy? I guess I'll put him over this because I don't really need this anymore. Um, transform transform deselect. Okay, so we have this. Oh, I think you can apply the condition to apply Stokes' theorem is to just have some cool shenanigans going on. This guy has a curl, so we can apply the theorem, I assume. Um, so, uh, ah, um, what am I looking at? So we have a curl, we have a curl, curl, S. So we put our curl here in like this little dot product of the surface integral, and that would be equal to, I want to change colors. That would be equal to the circulation of b dot dr, which is this is what we have right here, and they're saying that is equal to this. Hmm. Hmm. To get to this, we added this shenanigans for no reason, so we need to also add it to this side as well. To get these integrals, we summed up over. We're summing up across the surface, so we need to sum over here across the surface as well, which is why we have this and this. That just means we're summing up across the surface. Uh, so that makes sense. Everything comes down. Wait, S dot D. Yeah. I agree. I agree. Um, and now they're saying this turns into this. We pull out the constant. Yeah, I agree. And current density multiplied by area will just give us back the current. So yeah, I agree. This state. I wonder if you can hear my dogs. Probably, but I don't really care. So yeah, too bad. This states that the circulation of the magnetic induction is proportional to the total current passing through the surface enclosed by C. So we have a curve. Circulation of the magnetic induction is proportional to the current passing through the surface enclosed by C. So we have this current is proportional to the circulation of B inside the curve or around the curve. Where is this B? Circulation of B, the curl of B. I think just here, from here, the B is flow of the curl. Says that the circulation around the closed part equal to the flow of the curl across the enclosed area. Flow of the curl across the enclosed area. Circulation around the closed part. Circulation around the field. Circulation. This guy is a circulation. This guy is a flow of the curl. Circulation around the closed part. So B is in the part and the current is in the surface. I think that's important to note. B is on the curve, not inside. Unless it is. Is it? I don't. The way I read this, I don't think so. But maybe I'm illiterate. That is also a possible thing to take into consideration. Um, it states, I agree. It is worth pointing out that Stokes' theorem in the equation 1 point this thing that we have saved here is worth pointing out that that is valid whether or not the closed curve, yeah, obviously, lies in a plane. This means that in general the surface S is not a planar surface. S is allowed to be planar even when C is planar, because the small closed loop C can be taken out of the plane. That Stokes' theorem holds for any surface bounded by C. I assume this holds for like everything. Like whenever you have any, like, you can just apply this logic to anything. Like if you have a curved guy, just pretend he's flat. Just go really, really small. He's flat. This curved guy is just flat guys in disguise. Um, Maybe I'll take a break, a little small break, yeah. Hello. Um, Hello. Let me see if anyone is messaging me. Not a soul. Not one person. Um, like, well, if we zoom out, if we rewind, like a decade, few decades, that is not insane. That is just, that's not bad. Someone not messaging you for an hour, someone not talking to you for an hour, that's not something to go insane about. Um, so I don't really care. I don't care, I don't care, I don't care, I don't care, I don't care. I don't care. copium. Um, how long have I been streaming? Oh, hour and 10 minutes. Okay, we move. Operator identity. Stokes theorem. Stokes theorem can be applied to the vector field blah blah equal this. I agree. VR scalar field plus direction. I vector field VR equal. So you're saying that this vector field only points in one direction, like every single point in this field is EI. I think that's what it's saying. Stokes theorem can be applied to this to give uh, um, S. Okay, we have S. We have the D, this, we have the curl. There's nothing in there. There's absolutely nothing. Um, this is a nothing burger. Wait, what? Isn't isn't it S D sigma dot the curl shenanigans? Isn't it this? Why is there no dot here? Why is the curl including this guy now? I know that like for a determinant you can interchange rows. Maybe that's something to do with that. Like this is like A dot B cross C. You just put hmm hmm. Well what would be the other side of this? The other side would be phi dot dr nabla dr. I'm a little confused. I am a little confused. Okay, let's just compute this guy here. So the I component of this, wow, well, we're already in deep waters. I, J, K, D this, X, Y, Z, del X, del Y, del Z. Let's just go in normal I for now. The I component is D. I need to give myself more space. The I component is D this del Z minus D this del Y. This guy here is the x dy. This guy here is the x dz. If we're allowed to cancel, this would just be y. This would just be del Wait, what? If we cancel the Z and del Z, we just have del. Can we do that? Are we allowed to just have del? Del of what? Del of a scalar function. What does this mean? You change in this. Are we allowed to do that? Are we allowed to do that? Well, let me go back to here. I think we were allowed to do that here. And when we did that, dx, we had del by itself. Did we need this guy to be present in order to do that? Did we? Did we need this guy here? Del. I don't know how I feel about this. I I'm I'm gonna reluctantly say that it makes sense. You can have a del by itself. But I don't like saying that. So let's see if we're gonna avoid doing that. I'll ask. Hmm. I'll ask my good friend ChatGPT later. I actually have a way to well, not ChatGPT, Copilot. I actually have like it set up so I can ask on stream. Like watch. Boom. Copilot. Ooh. But I don't think this necessitates that. And it's kind of weird to ask. Like it's kind of hard to frame the question. Although I think I'm kind of good at it. But I don't think it's, I just don't really want to right now, is the real answer. So we have del. Wait, what? Um, so the I component is this. This. If we cross off the stuff we want to cross off, we have del minus del. What? What? Del minus del? No. Dx dz dz. No, we have dx as well. Dx del minus. Wait. dz dx what? We have 2 dx del, which is just 0. Hmm. I don't like this. I don't like this. I don't like this. Let's just restart. Stokes' theorem can be applied to the vector field bling to give this V-R-E-I. Let me just read this entire thing and we'll try and figure it out after. Since this is true for any I, it follows that if we sum up this for all the i's, well, for the 3 i's, I assume there's only 3 i's. Like, how would you get a fourth dimension? Spooky. Um, it follows that bling. Hmm. So we're not really dealing with the full guy yet. This is just a fraction of the guy. So we have this, we get this. This goes here. Circulation. Well, not circulation. Integration of positive closed curve. dxi. Hmm. Uh, Wait, I think this is just Stokes' theorem to go from here to here. I believe dr Stokes' theorem dr d. This is weird. This is weird. I think I might have to go try to find some logic with the determinant. This result generalizes Stokes' theorem to the operator identity this, where if you have this, you can just replace it with this. If you have this, phi, this, phi, for operations on any field in space. That is a big claim. It gives rise to identical theorems such as this, blah blah blah. We have this guy cross VR. We have this guy cross VR. We have this dot bling. We have this dot bling. And I think previously this is something like Green's theorem, but you know, what is the difference between this and this? What is Green's theorem? Green's theorem, surface, surface and volume. Okay, I see. Right now we're just dealing with curves and surface. Okay, once we get this, we can get this. Hello, Green. My boy Green is back. Okay, let's try again. So we have this. The normal, what I expected this to be was the was the this dot nabla cross, well, curl of VR, or maybe even fire VR. Let's go with V. I expected it to be like this. But what they're telling me is they have they have the cross being like this. And there's no dot here. But actually there is a dot. There's a secret dot here. Because this is the ith component. And this is the ith component. They just didn't put the little I here. So this is really a dot product here. Okay. So yeah, it's correct to say that this is the dot product of E and this. Okay, I feel a little relieved now. I pray that this makes sense. I pray that this interpretation works out. Otherwise, I'll have to come up with some other stuff. So, what I expected was d this x, d this y, d this c, dot del del x, del del y, del del z, vx, vy, vz. In reality, this is what we have, which is vx, vy, vz, d this x, d this y, d this c, Del X, del Y, del Z, del C. Okay, to get from here to here, we interchange these two rows to get the V's on top. And then we interchange these two rows to get the D's over here and the del's down there. So I think if you change a row, whenever you change a row, you add like a minus sign, right? So we change two rows, so that's minus minus, which means a plus. So this is equal to this, which means this is equal to this. Expectation equal reality. I I can agree to this. Yippee, woohoo, hallelujah. That's just for this side. Let me see if this side makes sense. Okay. Um, is this a part of Stokes' theorem? I assume it is. Or can we just like reason this out? That implies that Stokes' theorem has no reason. I'm not saying that, obviously. Okay, Stokes' theorem. We have this guy. Um, hmm. I'm just gonna pretend we're dealing with this. We have this. Stokes' theorem says that phi.dr, phi.dr, this thing here, which is nabla, nabla.dr, nabla.dr. What is dr here? Dr would be v here. So circulation, closed loop. No, not circulation. Integrating across a closed loop, closed curve, del dot v. And that is just, well, v only has an I component. So it'll just be del 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 x in the I direction, vi. No, not vi. Well, yeah, vi, but you can just say phi r. So we have the phi r here. We have del xi, not dxi. Hmm. Hmm. I'll just take their word for it. Like, maybe there's like a little, there's a small lapse in judgment from me. I'll just take their word for it. Okay. I've been streaming for an hour and a half. I think I should stop after I do, yeah, Helmholtz. I'm excited to get to this because I had some success with it, like in my first read, and I want to relearn it. Okay, let's go back. All right, example. If this equal this, Stokes' theorem for this vector field reads, um, there's no curls here, so right off the bat I'm confused. Well, I guess I guess to start off Stokes' theorem, we just need to imagine a loop, and then from there, it's automatically we can automatically once we have a loop and we have some vector field, we can apply Stokes, I think. So we have this. This is this. This dot dr. So there's no z component, so that's 0. The s components is dx and this dy and this makes sense. Equal. Now we apply in Stokes' theorem to change this into surface integral. Ah, Stokes' theorem. D plane, blah 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 plane. Gradient, cross plane. Yeah. Okay. So we're computing this into the three terms. So the x component dy to z, x component of this is, we'll figure that out after. Okay, so nothing fishy is going on so far. So unless some canceling goes around, this should be this, this should be this, this should be this. But I have a feeling there's some canceling. Maybe not though. This cross this. Do I need to do that? I'm tempted to just write out the determinant. But maybe I can just, maybe I don't need it. Maybe this is a crutch I need to overcome. And I'll cross this. Maybe it's a necessary crutch. So the x component would just be, x component means we're dealing with these guys. This is how I'm doing it in my head. We're dealing with these four guys. So it'll be like this. So del del y x component del y. What's the y component of? What's the z component? There is no z component. So this guy just disappears. So then we do minus del c of the y component of phi, which is phi, negative phi, which means which which is good because this was positive and we had negative from normal course of action, so it makes sense. Del phi, yeah, good, good. Okay, del dy component, the z component disappears. So all we're left with is minus del, not del, yeah, del, del c of this guy, del phi del c. Yeah, good. And yeah, it's positive because the minus on minus cancels out. And finally, we're left with the z component, which is um, we'll have two terms because um, the two zeros here don't really matter. So we're actually getting two terms this time. First off, we got del x of the y component, which is this, yeah, plus, okay, we have done minus makes up plus del Lx of the y. So right now we have minus del phi del x. Part of me is worried about this minus, but I shouldn't worry. I'll just trust in the system. Next up we have del. Wow, I pressed a button. Next we have del LZ. No, del y of the x component, which is minus. Oh yeah, I see. Yeah. This minus is only here because the two terms we get from here are both negative, so we can factor out the minus to get the sum of these guys. So yeah, I agree with this so far. Um, if Phi and Kai, like that's my dog's name. Is this Kai? I know Kai is like this, but is this lowercase Kai? Phi, Phi. I know all the symbols. I just forget. Is it Psi? I don't know. Yap. If this and this don't care about C, this simplifies to Stokes' theorem. Okay, we're dealing with a closed loop. We're dealing with a closed loop, so that's why they're talking about this. The result simplifies to both independent of C. Both independent of C. Delphi. So I think what they're getting at is, since this is DZ and LCs and stuff, they want to cross this out. Maybe. So we're just dealing with these two terms. Del x del x del phi dy del phi dy. Okay, this is. Let me come back to Earth. If this and this are both independent of Z, the result simplifies to this, independent of C. So right now, del chi, I don't know, del chi, del C. If this is independent of C, that means this change does nothing to this. So del phi del Z, del chi del Z is just chi. So it can just be chi dy dz. Um, what do we do about this dz though? Well, independent of C. What is this dz then though? Interface between two. What? What is going on here? Ah, okay, this is getting weird. Okay, del phi del C phi dz dx. Let's just work with what we have right here. The result simplifies to this. Minus. I think it's exactly what I was saying before, like at the very beginning. Like, we don't care about these for some reason, and we're just left with this. Because this is just this combined with this. So we literally don't care about this guy. Why do we not care? Del phi, I keep saying phi. Del chi, del c, dy, dc, independent of z. independent of C. Change in C does absolutely nothing. Del this, del C. Change in this, change in C. Does this just mean this is phi? This is chi? dy dz? The other thing you could possibly do is just um, cross out this and this to be left with del chi dy. Um, hmm, hmm, hmm. This is known as Green's theorem in the plane. It is well past an hour and a half, so maybe I should just end. Hmm. I agree with this, but shouldn't there be something left over? Okay, well, let me just have peace of mind. Let me try to get this somehow. Okay. Um, is this just I was gonna say, is this just Stokes' theorem? But I assume not because they're calling it Green's theorem, so it can't be Stokes' theorem. Unless they literally have the exact same theorem. So we start over this. We're dealing with a surface. We're dealing with a surface, which is also just a curve. Along the curve, we have bling dx. But this is just circulation, right? This is just circulation. Like, blung, blung, blung. There's a minus here though. Why is there a minus here? Is it just because this is a minus here? I think it is. Hmm. Yeah, I think that's the case. Because even if it was just plus, this times this, there's still a minus here. So they're just getting rid of the bracket. Circulation is actually circulation this time, not just integration across a closed curve. Um, it looks really similar to Stokes' theorem, I have to say, because one is a circulation and one is dealing with like the stuff with the area, the surface area. Ah, hmm. This is known as Green's theorem in the plane. Maybe it's just called Green's theorem because the stuff in here looks kind of complicated, and they don't want to be like, this is also Stokes' theorem, and confuse students. Do they cater physics towards students? Do they cater physics towards the layman to understand? I don't think so. It's all about just having a deeper understanding. But I guess it doesn't hurt to be user-friendly. I think I think I've done enough. Um, Next stream should be Helmholtz, and hopefully we start this. I assume it's kind of big. It is. I shouldn't be scrolling. I shouldn't be scrolling because copyright. Um, that is the end of stream. Farewell, farewell, my friends, farewell. My zero friends. All of you. Thank you so much. Thank you.